Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 3.1.1, which is using an area model. And in this chapter, we actually take a bit of a departure from all of the geometric theorems and such, and we actually get into what those area models that we've been studying this whole time, one of their practical applications. And one of the practical applications of these area models is to be able for us to predict probability of events happening. And so the first problem in here, 3-1, talks about genetic traits, similar to a Punnett square that you would encounter in biology. And in this case, they're looking at very specific traits, the ability to bend your thumb backwards and the ability to roll your tongue. And so it says, according to the table, what is the probability that a randomly selected person from the U.S. would have both special traits? In other words, they can roll their tongue and bend their thumb back at the same time. Well, in order to answer this question, we need to go to this area model here and figure out what each of the areas would be. Now, luckily, the area of a square is pretty simple because what you have is you have a 1/2 chance that it would be yes, you can bend your thumb, a 1/2 chance it would be yes, you can roll your roll your tongue, and so that means that the probability of those guys together would be 1/4, and luckily all of them are 1/4 because of that whole base times height aspect of the area model. So when we get to this question here, what is the probability that someone can do both, bend their thumb and roll their tongue? Well, what I'm going to look for is I'm going to look for the intersection of these events happening. So this red vertical line would be all people who can who can bend their tongues, and then this horizontal line here would be all people who can roll their tongues. And where those guys intersect each other is going to be 1/4. Is going to be 1/4. And so the probability that you would find someone that can do both, roll their tongue and bend their thumb, is going to be 1/4, or 25%. In part B, it talks about, according to this table, what is the probability that the person has only one of the special traits? And we have to justify our conclusion. This is going to be a little odd because most people are going to try and look towards the yes portion of each one, but actually where our information comes from is it comes from the no portions, right? The no portions of each section. Because the two things that I just circled in blue, this 1/4 of the population in the top right corner is able to roll their tongue but not bend their thumb, right? So they have one of those special abilities. The other 1/4, which is down here, can bend their thumb but cannot roll their tongue. So hopefully it makes sense why I'm pulling from the no portions of these boxes. And so if we're going to look for either one of these things, it looks like it's going to be a probability of 1/4 or 1/4 here. And again, if we think about the person only having one of these traits, they can either do bending their thumb or rolling their tongue. But I'm going to be selecting from one or the other of these boxes here. So hopefully it makes sense that the probability of that happening would be 1/2, right? Because I'm selecting from literally half of the boxes. And the only way that can happen is if I add those guys together. So hopefully that part B makes sense. And when it comes to probability, you want to pay attention to the language, especially when you hear things like and or. And in the next couple lessons, we will go over more about what that means. But for now, hopefully you can start establishing a pattern, the notion that and produced the 1/4 because of the intersection of the two pieces of data, but the or produced an addition, which was what we call the union of the data. But we'll talk more about that later. In part C, it says, this table is very useful because every cell in the table is equally likely. Therefore, each possible outcome, such as being able to bend your thumb but not roll your tongue, has a 1/4 probability. And it says, however, this table assumes that half the population can bend their thumb, but in reality, only about 1/4 of the U.S. population can bend their thumb and 3/4 cannot. It also turns out that more than half, 7/10, can roll their tongue. How can this table be adjusted to represent those percentages? Discuss with your team. Okay, so what they're asking for in part C here is they want us to redraw this diagram. I'll also go and switch colors here. They want us to redraw this diagram. So this is the bend thumb. So the bend thumb. And this is the tongue. And again, we'll split this up into yes, no, And so the way this can be adjusted is instead of 1/2 for the bending the thumb, we can actually say this will be 1/4 and 3/4. And then from here, 7/10 of the people can in fact roll their tongue, but 3/4 cannot. So how does this affect probability? Well, it means that not every one of these boxes is 1/4 anymore. For instance, here, this is going to be 7 out of 40, right? Because 1/4 times 7/10. And again, this is where that area model's practicality comes in. The next one's going to be 21 over 40. And the next one's going to be 3 over 16. And the next one's going to be 9 over 16. So to put that in perspective, each of these numbers comes out to be those percents. 17.5 can do both. 52.5% can roll their tongue but not bend their thumb. 18.75% can bend their thumb but not roll their tongue. And 56.25 can do neither of the two. So hopefully that makes sense in the first problem. We'll move on to the second one in just a second. And we're back in section 3-2. In part A and parts A, B, and C, they're actually asking about both white and purple diagrams. Now, the purple diagram might actually not be that necessary. I just wanted to give you all perspective as to what these numbers actually meant, because it's hard to, especially when the denominators are different, it's hard to determine off the top of your head which numbers are the largest. So I converted them all to percents. So just to let you guys know, 7 out of 40 is 17.5%, and so on and so forth, looking at each of the corresponding boxes. In part A, it reads, how can the diagram be altered to show that 7/10 of the population can roll their tongues? And copy this diagram into the paper and create 2 rows that respect this probability. What they're asking you to do in part A is not draw the purple diagram or the white diagram where all 4 boxes have actually physically equal area. They want you to actually split it so that it looks like this. And so honestly, I don't see much of a payoff in making it look like this, where it's 7 over 10 and 3/4 right here. Honestly, there's no payoff in that. I would say just keep all the boxes the same and use your number sense to determine which one's larger and which one's smaller. So that would be A. They're asking you to draw the box actually to scale. Not a whole lot of payoff there, so I think we'll pass. It says the areas of the regions represent the relative probability. So you're supposed to physically see that the 7/10 version, why don't I just finish it because we're already there. So the 7 out of 40 is supposed to be larger than the 3 over 16. So I guess without doing percents, you should be able to tell which one has a larger probability. Again, the 21 out of 40 is supposed to be larger than the 9 over 16. And so it says, for example, the portion of the probability area model representing people with both special traits with a width of 1/4 and a height of 7/10. What is the area of the rectangle? Well, the area of that rectangle with the 1/4 here and the 3/4 here, the area is 7/40ths, and the area means that the probability of getting a person who can do both, in fact, I'll type this out. So the area represents the probability that a person with both traits will be selected. Right? That's what that's trying to say, and I'll move that right here. Barely enough space. Okay, so actually I'll just move it down here, and I'll just put a B in front of it. That way you guys know which one I'm talking about here. There you go. The area represents the probability that a person with both traits will be selected at random. So part C says, what is the probability that a randomly selected person can roll his or her tongue but not bend his or her thumb back? Show how you got this probability. Okay, so again, we're trying to say they can roll their tongue, right? So the tongue part is the yes right here, right? This is the row for the tongues, but they cannot bend their thumb back. And so that's going to be a no for the thumb. So where do those two probabilities intersect? It's going to be 21 out of 40. So 21 out of 40, or as we convert it to a percent, that would be 52.5% of people. And again, if we had to justify it, we could say because that box is where the yes for rolling but no for bending intersect. But no for bending intersect. And that would be how we got it. So 21 out of 40 or 52.5%. So that's 3-2. I'll be back with 3-3. And we're back with problem 3-3. And after a lot of exposition about probabilities in vain, what you'll come to realize is that this question is having you deal with two Navajo persons, and you're trying to test their blood types, and you're going to try and find out the probability of finding a Navajo person with a particular blood type. And so after a lot of exposition there, they're telling you that 73 out of 100 Navajo persons would have a type O blood type, and 27 out of 100 Navajo persons would have a type A blood type. And so in part A, it says, suppose you select two Navajo individuals at random. What are the probabilities for the types O and A for the two individuals? This time, drawing an area model that is exactly to scale would be challenging. A probability area is useful because it allows you to calculate the individual events without drawing it to scale. Basically, what I talked about before, drawing it to scale is actually kind of pointless. Just draw them as rectangles. It just makes your life easier. And so from here, I actually calculated, well, I didn't calculate anything, but the answers are in here. But let's talk about how they got these numbers. So this number here that says the probability of a Navajo person from person 1 having an O blood type is 73 over 100, and that intersects the notion of the Navajo person 2 having a blood type of 73 over 100 or type O. And the way we get this area is the base times the height, or 73 over 100 squared. Some people might call it 73 over 100 times 73 over 100. It's the same thing. Likewise, this box here is going to be 27 over 100, which is the base of this rectangle, times 73 over 100. And if you calculate that into a percent, you'll get 19.71. This guy unimaginatively will be the same thing, times 27 over 100, and then this guy will be 27 over 100 squared, or 27 over 100 times 27 over 100. So real quick, that's how you get each of those numbers here. It's just the area of each individual box, which then answers question A. Question B says, what is the probability that two Navajo individuals selected at random will have type A blood? And then it says, what is the probability that they will have the same blood? Okay. So let's talk about just two Navajo persons or two Navajo individuals having type A blood. So how do we do that? Well, the probability of the Navajo person 1 having type A blood lies along this column right here. And that's just person 1 Navajo having type A blood. Person 2 Navajo having type A blood comes from this row right here. So what you're looking for, and what this problem is trying to slowly teach you, and all the probability problems in this section are trying to teach you, is when you're looking for two events happening at the same time, where they're surrounded by an and, a person with type A blood and another person with type A blood, you're looking for the intersection of the two events. And in other words, where the two red lines are going to cross. So the two type A bloods, so type A, that's going to be 7.29%, because that is where a probability of person 1 meets and intersects probability of person 2. Now, the same blood type, the same blood, well, they could have both type O or they could have both type A. So again, we're looking at this probability as well as this probability. So the two probabilities combined would actually be 53.29 plus 7.29, which ends up being 60.58%. 60.58%. And again, it's these two events happening, one or the other. Again, what is this problem trying to teach you? Is that when you see the word or, you should start making sense of the fact that addition seems to be involved. And we saw that in the last problem here. This number was obtained by 27 over 100 times 27 over 100. And notice how this problem contained, once again, the word and. So you're supposed to be seeing that pattern happen right now in real time as you do these problems. Let's go to 3.4 real quick, and then, or 3-4, and we'll keep on going with this section. And here we go in 3-4. They talk about shipwrecked, and here's the thing about all these probability problems is that there's so much exposition that needs to happen, so feel free to pause and read about the problem about the 4 blood types and Nick and Zach and all of them. But part A, without wasting too much time, it says, make a probability area model representing the blood types in this problem. List Nick's possible blood at the top and Zach's possible blood on the side, just like the table. Without taking up too much time, bam, there you go. And again, how did we get all these numbers? We multiplied those areas together, right? 0.45 times 0.45 is 20.25 and blah, blah, blah. Here we go. So it says, what is the probability in B? What is the probability that Nick and Zach would have the same blood type? Well, here's the thing, is that they could both be O, or they could both be A, or they could both be B, or they could be both BAB. So from here, that's going to be 20.25 plus 16 plus 1.21 plus 0.16. And these are all percents here. And so from here, that number ends up becoming 37.62%. And so again, what did we do? We looked at each of these individual events happening. 4 of the squares have the likelihood of happening. Each square has a different probability. Again, there's that word or again, right? Where the or led to us adding things together. Just kind of pay attention to that. It says, luckily, 2 people do not have to have the same blood type for a receiver of blood to survive a transfusion. Other combinations will work as shown in the diagram to the right. Now, the diagram to the right is actually really confusing, but I will go ahead and copy that in there. Give me a second. And here's our cool diagram. Basically, what it's saying is that O can go into A and to B and to AB, but only A can go to AB and only B can go to AB. Honestly, I had an easier time figuring out the sphere grid in Final Fantasy X, but anyway, we'll talk more about that as it comes up. From here, it says a person with type O blood can donate to anybody. A person with type A blood can only go to A or AB. A B type can go to B or AB, but only AB can go to AB. That actually, the description makes more sense than this diagram, but that's okay. So it's saying, assuming Nick's blood is compatible with Zach's in other ways, determine the probability he has the type of blood that can save Zach's life. Okay, so what this problem is trying to say is that this is condition 1 right here. If Zach has condition 1, then he can receive an O, an A, a B, or an AB. Okay, cool. So that's going to be 20.25 plus 18 plus 4.95 plus 1.8. But if Zach is type A, then it looks like he can only receive A or AB. So that's going to be plus 16% plus 1.6%. Right? So again, all of these are independent situations. They're or that could happen, right? I'm just going to be adding up the red circles. If Zach is B, then he can go B or AB. So that's going to be 1.21 plus 0.44. And if he's just AB, it's going to be 0.16. So what did I do again? I added up all the red circles together because they're all separated by an or. It could be this guy or 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 so on. And ultimately, I'm going to add all those things together because we keep seeing this pattern, right? When or is used, addition seems to be the thing. So I'm going to add up all these numbers, and I'm going to get 64.41%. There's a 64.41% chance that Nick and Zach will have a blood type that will be compatible to transfuse into each other should the possibility take place. Okay, so again, what are these problems trying to teach you? They're trying to teach you how to find individual areas and how those areas will apply towards finding probability. So let's finish up with 3.5 and then we'll be all set. And to finish up the last problem here, it does say you made a critical assumption in 3-4 when you made the probability area model and multiplied the probabilities. And so let me move this guy down a little bit here. It says blood is affected by genetic inheritance. What if Zach and Nick were related to each other? What if they were father and son? How could that affect possible outcomes? Well, remember, inheritance by genetics is not random. So, in order for, if they were related and it affected how could it affect their possible outcomes? It means that if they are related, then the samples are not random. And that affects the probabilities of each event. Genetic, or rather their relationship, would impact the probability that they share the same blood type. And therefore, each event would not be independent. In other words, one event could cause the other to happen, which is how it would affect the probability. So in other words, to answer part B, it says what needs to be true in order to assume a probability model will give an accurate theoretical probability. The reverse of this needs to be true, which is that each event needs to be independent of each other to give accurate theoretical probability. In other words, one event can't affect the other one happening for us to get accurate probability. Cool, that should wrap up this lesson. And so, as always, leave comments or questions in the comment area, and I'll see you all in the next episode.